Why skyscrapers sway in wind but never fall. You're standing on the 80th floor of a skyscraper. The wind outside is doing 90 miles per hour, and the building is moving. Not shaking, not cracking, moving. And the engineers who built it, they planned it that way. Most people assume skyscrapers are built to stand completely still. Rigid, unmovable, like a rock planted into the ground. That assumption is wrong. And if buildings were actually built that way, stiff, inflexible, unyielding, they wouldn't survive a single major storm. They'd crack from the base and collapse within years. The real secret behind why skyscrapers survive isn't strength. It's something most people never expect. Stay with me, because by the end of this, you'll never look at a tall building the same way again. Here's what actually happens when wind hits a skyscraper. Wind isn't just air pushing against a surface. At height, wind moves in massive, invisible waves. Gusts don't hit evenly. They slam one side, create suction on the other, and generate something called vortex shedding. Vortex shedding is when wind wraps around a building and creates alternating spirals of pressure on each side. Left, right, left, right. Like an invisible hand pushing the building back and forth in rhythm. At ground level, you'd feel nothing. At the 60th floor, that rhythm can build up. And if the frequency of those wind vortices ever matches the building's natural frequency, its own internal vibration, you get resonance. Resonance is what destroyed the Tacoma Narrows Bridge in 1940. Wind hit the bridge at just the right frequency. The bridge started oscillating. Engineers watched it twist and ripple like a ribbon. Then it collapsed into the water below. A 2,800-foot skyscraper facing the same physics. That's the problem engineers had to solve. So how do you stop a 400,000-ton building from shaking itself apart? The answer is sitting at the very top of some of the world's tallest towers, and most people walk right past it without knowing it exists. The obvious solution seems like, build it stiffer. Use more steel. Make it stronger. Engineers tried that logic early on. It doesn't work. Here's why. When you make a structure completely rigid, it can't absorb energy. So when wind hits, all that force has nowhere to go. It transfers directly into the structure. Stress builds. Materials fatigue. Over time, cracks form in places you can't even see, deep inside the steel connections, the welds, the concrete core. A rigid building doesn't bend, it breaks. Nature already figured this out millions of years ago. Look at a tall tree in a storm. The trunk flexes, the branches move, the roots hold. The tree doesn't resist the wind, it works with it, dissipating energy through movement instead of fighting it. Skyscrapers had to learn the same lesson. At the top of Taipei 101, once the tallest building in the world, there's a steel ball. It weighs 660 metric tons. It hangs from cables like a giant pendulum, 92 meters above the ground, suspended between the 87th and 92nd floors. Tourists can actually see it through glass walls. This is called a tuned mass damper. Here's how it works. When wind pushes the building one direction, the ball swings the opposite way. The movement of the ball counteracts the building's sway. It's essentially a counterweight designed to move out of phase with the building, always pushing back against whatever direction the building is moving. During Typhoon Soudelor in 2015, Taipei 101 swayed nearly a meter. The damper swung over a meter in the opposite direction. The building stayed stable. No structural damage. 660 tons of steel, doing nothing but swinging and saving a skyscraper. The damper in Taipei 101 is the most visible example. But it's not the only solution engineers use, because some buildings face a different problem entirely. Wind isn't just about side-to-side movement. In certain locations, the ground itself moves, and that changes everything. In earthquake zones like Japan and California, engineers face a double threat: wind and seismic activity. The solution they developed sounds almost too simple. They put the building on rollers, not literally wheels, but a system of base isolators. These are layered rubber and steel pads installed between the building's foundation and the ground. When the earth moves, the isolators absorb and redirect that energy. The building above barely feels it. One hospital in Los Angeles was built with base isolation specifically so it could remain operational during a major earthquake. During the 1994 Northridge earthquake, a 6.7 magnitude event, the hospital stayed fully functional while surrounding buildings crumbled. But base isolation alone doesn't handle wind sway at the upper floors. So engineers combine systems, base isolators at the bottom, tuned mass dampers at the top, and in the structure itself, a carefully engineered core and outrigger system. The central concrete core acts like a spine. Steel outriggers extend from that spine to the outer columns like ribs. This distributes lateral forces across the entire structure instead of concentrating stress at any single point. The building can flex, controlled, calculated flex, without any single joint taking too much load. Here's something most people never realize. The shape of a skyscraper isn't just about aesthetics, it's aerodynamics. The Burj Khalifa, tallest building in the world at 828 meters, has a spiraling, Y-shaped cross-section. As you go higher, each floor rotates slightly. This isn't a design choice. It's an engineering decision. That spiral shape disrupts vortex shedding. Instead of wind wrapping around a consistent surface and building rhythmic pressure, it hits changing angles at every level. The vortices never sync up. Resonance never builds. Wind tunnel testing for the Burj Khalifa involved over 40 different building shapes before engineers settled on the final design. They were essentially tuning the building like an instrument, finding the shape that would never vibrate at its own natural frequency under wind load. The Shanghai Tower takes it further. Its twisting form reduces wind load by 24% compared to a standard rectangular tower of the same height. That reduction saved over $30 million in structural steel costs. The shape of the building is engineering. So next time you look up at a skyscraper and see it standing perfectly still against a storm, know that it isn't still. It's swaying, calculated, controlled, alive in a way rigid structures never could be. 660-ton pendulums swinging in the dark. Rubber pads absorbing earthquakes. Spiraling floors breaking the rhythm of the wind. Skyscrapers don't survive because they're strong enough to resist. They survive because they're smart enough to move. Subscribe. Next video breaks down the engineering that stops a 200 mph train in under a mile.